All right, so we're picking it up where we left off with our discussion about areas and volumes that are being calculated with integrals. So last time we saw how to calculate the volume rather, of a solid shape like a cube or a rectangle, not a rectangle, a sphere or possibly a pyramid, or any of any many other possibilities. So basically, what we were trying to do was take functions that we already understand. Like, for example, we know how to calculate the volume of the sphere, we know how to calculate the volume of the cone, and we know how to calculate the volume of the pyramid. So calculating the volume with integration is a very straightforward matter. What you're effectively doing is finding a cross section, which in the case of the pyramid is the base, and then you are taking the area of a series of slices and coming up with your volume. Now, you can see here in this diagram, we sliced through a solid, and we figured out its area. We multiply that by the delta x's, and what we end up with is a volume that consists of the products of these areas times these delta x's, which are the widths of the cross sections. Okay, now we know that this is only approximately correct, but if we take the limit and we allow the number of cross sections to go to infinity, which implies that the delta x's are converging to zero, we'll end up with the correct value when we take the integral over that interval from a to b. So this is the so-called slicing method, because we're taking each solid and we're slicing it through the cross section and using that to come up with a formula for taking or calculating the volume. There's other ways of doing this too, of course, but this is a very straightforward way. And the last time we saw how this is done with a pyramid, where the base of a triangle, or the triangle itself could be thought of as a cross section, and we use the geometric properties of that triangle to come up with a formula for finding the volume of our pyramid using integration. Okay, now we're going to try something a little different. We're still going to be looking for volumes, but this is a little bit different because we're not taking standard shapes like pyramids, for example. We're creating different types of solids by rotating a function around either the horizontal or the vertical axis. So what do I mean by that? All right, well, let's start with the case where we have a function of some kind. This red line is a function. And we can see that the shaded region is the area under the curve between the function and the horizontal axis. And if that's all we wanted to know, well, we've already seen that that shaded region could be calculated as the integral from a to b, whatever the interval happens to be, f of x dx, and we'd be done with it. But since we're interested in the volume, what we're actually doing is we're taking this curve and rotating it around the horizontal axis. And you can see in the bottom, it's about halfway around. And then this is the final product. It kind of looks like the Apollo space capsules now that I'm looking at it. But it could be considered a type of cylinder, I suppose, or a flower vase. I don't know. There's a lot of things that it could be used for, I suppose. But or the top of a Coke bottle. There's all kinds of possibilities. But the important thing here is that we don't have a formula for this shape. But what we do know is the radius of the cross section, which is itself a circle. Okay, in other words, we can think of this as our cross section, or the slice that we'll use, and the radius would just be the height of this function from the horizontal axis up to f of x. So that's the radius of the circle, which is itself the cross section of this shape or solid. Okay, now that is going to help us figure out the appropriate volume. Okay, so let's look at a specific example. Instead of that one, let's use this one. We're going to take a parabola, f of x equals x squared minus 4x plus 5, and then we're going to rotate it about the horizontal axis between the interval 1 and 4. Now we've seen this before, and again, like I said, if we were only interested in the area under the curve, it would be a simple matter of taking the integral from 1 to 4 of x squared minus 4x plus 5 dx. Okay. But since that's not what we're looking for, it's more complicated than that. And so let's see how this works. So we're going to do the rotation. Now you can see what it looks like. Let me just make this a little bigger so you can really see it. Now, I don't know how you would describe this shape, but what's clear from looking at this is that the cross sections are circles, okay? And the height of this, or the radius, is just the difference or distance between this function or parabola and the horizontal axis. Now, as we saw earlier in the chapter, if you think of the horizontal axis as g of x, then the radius, or the height, the radius itself would be simply f of x minus g of x. But of course, g of x is 0 across the horizontal axis. So the radius is simply f of x x squared minus 4x plus 5. That's the radius. Now, if you recall, the area of a circle is pi r squared. So for this particular case, the area is pi times x squared minus 4x plus 5 squared. And because we're using the slice, we're using slices to come up with this volume. What we're going to need is to calculate the volumes here of these slices is we're going to define delta x to be the width of the slices. And so that means that the volume could be calculated as pi r squared dx. Now, oh, by the way, don't forget, when delta x, the limit as delta x gets smaller is this dx, which is an infinitesimal change in dx. So in other words, remember we had this earlier, v is approximately equal to the area of each of these slices times the delta x. Okay, so in other words, if we took that shape and visualize that we're breaking it up, let's see, how can we do this? They're basically slices, each of which has the same width, delta x. If we just add it up the way it's written here, we will get approximately the correct answer, but we know that that's not exactly correct. So what we have to do is take the limit, the integral rather, over that interval to come up with the correct value. So now it's a pretty straightforward process. I mean, all we're doing is calculating a definite integral. Now, the only tricky part here is that we have to square a quadratic equation. So here's a technique that I don't know. This is something that I've asked my classes about before. If anybody has done it this way, 4x squared minus 4x plus 5. The way I was taught to do this is to line them up. And now what we're going to do is multiply every term by every other term. In other words, I'll multiply these, and then these, and then these two. Now it's going to get a little messy, but minus 20x plus 16x squared minus 4x cubed. And then the x squared gets multiplied by all three of these, so we'll have 5x squared minus 4x cubed. And then at the end, we'll have x to the fourth. Now they're all lined up. So I'll have x to the fourth minus 8x cubed plus 26x squared minus 40x plus 25. Now, I don't know if there is another way of doing something like this. We can't use FOIL here because FOIL only works when there's two terms in each expression. I don't know any other way of doing this, but you may have seen something. But I kind of like this approach because you can see exactly what you're doing step by step. So when you're multiplying two polynomials like this, you can just line them up and multiply each term individually, and you should be able to combine them into the correct answer. So that means that what we actually have here is this catastrophe. And now we have to evaluate all of these individually using the power rules. In other words, x to the cube. All right, actually, we don't need to do them all separately, but so you get x to the fifth over 5 down here. Evaluate from 1 to 4. Notice how I moved the pi outside, by the way. Now x cubed will become x to the fourth over 4, which you see here. X squared becomes x cubed over 3. X becomes x squared over 2, and then here we simply have dx, that becomes x. Now, I didn't write out all the intermediate steps, but I mean, you know what we're doing here. This is, for example, 4 to the fifth minus, sorry, 12. I don't have that much space here, so let me just show you a little bit of this. We have pi, 4 to the fifth over 5 minus 1 to the fifth over 5, et cetera, et cetera. So you can confirm that on a piece of paper, but these do actually wind up adding up to 78 pi over 5. So the strategy here wasn't really much different than what we were doing earlier with the standard shapes, like the standard solids, I should say, like the pyramids and the cones and and all the rest. What is different is the way you come up with this volume. You're simply, again, taking the radius, which is formed from the original function and the horizontal axis. That is going to give us the area of this cross section. And then once we provide the delta x, we get a series of volumes, which we can calculate by integrating. So all the methods or the revolutions of solids are done in the same way. The only thing that can change is that sometimes it's done with respect to the x-axis, and sometimes it's the y-axis. But that was true before too. I mean, we saw that areas below the curve could be thought of as with respect to the x-axis or to the y-axis. So the technique that we just learned can be summarized in a nutshell. It's when you look at it like this, you can see it's very straightforward. This is the so-called disk method. We're slicing the solid into a bunch of disks. Okay, so in other words, this is a circle. You show the width of this thing. Instead of a circle, what you have is a disk. Okay, So all it is the integral of the interval of interest pi f of x dx squared, f of x squared dx. Okay, but this implies that the function is rotated about the horizontal axis. What if that's not true? What if we rotated it from left to right instead of top to bottom? Then we have to make some changes. Okay, so let me copy this to the next slide so you can see these side by side. And again, we've seen something like this before. We saw what has to change when you are looking at areas below a function down to the x-axis versus to the left of a function all the way over to the y-axis. So essentially what you're doing is you're changing f of x into a function of y, and then you're integrating, with respect to dy. So let's look at a simple case, relatively simple case. We have got g of y is radical 4 minus y, and it's being rotated about the vertical axis. So this is approximately what it looks like. So the original function is here in the upper left-hand corner. Here's the slice that we're interested in. And then we start to do the rotation. And ultimately we end up with this piece. So this is actually meant to represent, the rotation, because if you notice, we once again have a disk. We have a circle, and here's the radius. And then here's delta x. And so we're going to just simply rotate it, but not just at that point. We're going to rotate the entire shaded region here. In other words, because the interval of interest is 0 to 4. So that means when you rotate it around, you'll end up with this. And it's kind of like, it's very cone-like, I guess, except that the top isn't pointy. So what do we do about the volume? Well, let's see. Here's the function. And now remember, g of y is radical 4 minus y. Now, of course, it's being rotated with respect to the vertical axis. And but all along the vertical axis, x equals 0. So this is what you're actually doing. Now, the interval that we're interested in is from 0 to 4. G of y is 4 minus y. Now, that makes things a lot simpler because that indicates that g of y, since it's radical 4 minus y, g of y squared is simply 4 minus y. Okay, now, and again, just as a side note, actually, no, this is fun. We don't have to worry about signs. So we just ended up with 4 minus y. So that means we can rewrite this as here's our pi, here's our g of y squared. And of course, here's dy. So it's a very straightforward one. And that's always kind of nice. We keep the pi on the outside. We break this up into 2 parts, 4y. And actually, you know what I should have done? There we go. And then you can see that when this one is integrated, it becomes 4y. And this one becomes y over 2, y squared over 2. Now the pi is still on the outside, so keep it out there. Here I've moved the -1/2 to the outside. And so I ended up with 4 times 4 minus 0 minus 1/2. Now here, what you've actually got is 4 squared minus 0 squared, 16 minus 0, or 16. And so you end up with 4 times, pi is multiplied with this one becomes 16. This is -8. So ultimately you wind up with 8 pi. So basically the two techniques are the same, except in one case you're integrating with respect to x and the other with respect to y. So now if you notice, the problem gave us the function in terms of y in the first place. We didn't actually have to do that part ourselves. Once before we had a problem where we were given f of x, we had to turn it into g of y, but it wasn't very difficult. So once you have the function in terms of y, using the disk method, all you're doing is taking the integral of the interval of interest of pi times either f of x squared or g of y squared, and you're done. Okay, now there's one more case we need to consider. This is going to take a different technique. Up to this point, remember, we've been using the so-called disk method. It's basically you're taking slices and then rotating them, essentially. What about cases like this? You've got a region bounded from above by f of x, from below by the x-axis, from the left and the right by 2 different lines. And let me show you what this looks like. So what we're looking at is this piece. And again, we know how to calculate this area. From whatever it's a to b, f of x dx. But here's what's going to happen. We're going to rotate it. You can see what's happening. And we're creating a type of cylinder, but if you notice, the top isn't flat. Otherwise, we could just take out the volume of the cylinder formula and we'd be all set. But unfortunately, because of the way this thing is shaped, the top is not flat. It's kind of like got this depression. It's almost like a candle that's partially burned down. Here's the wick. Here's the flame, and you can see it starts to melt in the middle there. So we need another technique. And this technique is often called the shell method, by the way, because the shape itself is defined not as a cylinder as such, but as a cylindrical shell, it's called. All right, so just remember, this technique we started out with is called disk. This one is shell. And this is how it works. So ultimately, taking into account that you're going to have areas and delta x's, what we're going to do is take the limit of this expression, and ultimately this is what we're after. Okay, so it's actually a pretty simple extension of what we were doing with disk, the disk method. All right, so let's look at a quick example. First, let me show it to you. And so you can see the function is f of x equals 1 over x. It's bounded between x equals 1 and x equals 3 and the horizontal axis. And if you notice, it's being rotated this way. So it creates what we're going to call a cylindrical shell. Okay, so based on the formula I just showed you a minute ago, let's figure it out. All right, so this is the basic formula. So we call f of x in this case is 1 over x. We wanted to know the volume between, we have 1 and 3. So we have the integral from 1 to 3 of 2 pi x 1 over x dx. Now look how nicely that turned out. You've got these cancel out. So you got the integral from 1 to 3 of 2 pi dx. Let's move the 2 pi outside. You've got the integral of dx, which means you just wind up with 1, x rather. So you've got 2 pi, x is evaluated from 1 to 3. Which means you basically just have 3 minus 1 or 2. So you can see that over here, 2 pi times 3 minus 1 is just 4 pi. So the technique is, I mean, it looks a lot scarier than it is. You've just got a handful of key formulas. And also you have to make sure you know when to use each technique. Okay. But basically the integration itself is not that difficult. I mean, unless you're given some horrendous formula, which we won't run into that. But anyway, so you can imagine, now all of a sudden, we need to know what happens if we rotate this around the horizontal axis. So you notice these are different than what we saw with the disk method. The disk method, we rotate around the x-axis, we had dx. Here we're rotating about the x-axis and it's dy. But you can see the similarity to this one. Yeah, let me just copy this in here. The only thing that's different is, well, there's a few differences. This is x and y instead of x, g of y and dy. Okay, and of course, these intervals will be different too. All right, let's consider this one. We have a fairly straightforward example. The function will be g of y equals 2 radical y. Bounded by the y-axis this time from 0 to 4 and revolve up and down. In other words, around the x-axis. So again, you have to see the pictures to understand this. This piece is being rotated, and this is what we end up with. So again, it's a shell, a cylindrical shell. All right, well, luckily the function is very straightforward, 2 radical y. So and one more thing, with respect to y, the interval of interest is from 0 to 4. Okay, so here we go. This is the original formula. From 0 to 4, we're integrating 2 pi. Now, this is the y. This is the g of y. And when you multiply, you can't really simplify them too much, although you can and you can't. Here's what's going to happen. So you can certainly gather together all the constants. Now, since radical y is y to the 1/2, what you ultimately wind up with is 4 pi y to the 3/2 power. And then, so that's what we have here. And also, if you notice, the 4 pi has already been moved outside. But now it's very straightforward because the integral of y to the 3/2 dy is y to the 5/2 power over 5/2, or 2/5 y to the 5/2 plus c. Okay. So we already knew that from the power rules. So let's do that here. It's a bit of a mess, but it's not that bad. So the 4 pi stays outside. The integral, the range of from 0 to 4. And by the way, now, of course, here I kind of skipped a step. Show you what happened, 4 pi. So what you're actually doing here is moving the 2/5 on the outside. And so now you've got 4 pi times 2/5, that's 8/5 pi. And then inside here, we only have, inside the brackets, we only have y to the 5/2 evaluated from 0 to 4. So the limits of integration are from 0 to 4. And so this stays. So now you've got 4 to the 5/2 minus 0 to the 5/2. Now, you're probably wondering, what is 4 to the 5/2 power? This is actually the square root of 4 raised to the 5th power, which means 2 to the 5th, which is 32. Now, if you didn't get that, you can certainly go to your calculator and ask for 4 raised to the 5/2 power, and it will certainly give you the correct value. But it's nice to know algebraically where it came from. So you've got 8/5 pi times 32 minus 0. This one is 0, of course. And so ultimately you end up with 256 pi over 5. All right, so that kind of wraps up our discussion about areas and volumes. These are very traditional calculus topics. Now we're going to move on to, and like I said, unless you end up getting involved with architecture maybe, or it used to be that graphic design was very heavily mathematical because the software didn't really exist like what we have now, and a lot of the techniques were being based on these very advanced equations. So, I mean, this might be useful in physics, I suppose, but certainly not in any business-related application. What we're about to do next is very, very important in finance and economics and other business disciplines, because we're looking at integration over exponential and logarithmic functions. So that would be what we call part 2C. So this part is done. And so I'm going to open up 2C. And we'll get as far as we can today, and we'll carry on with this tomorrow. This is not a huge section, but there's a lot of material here, a lot of important material here. And everything we're seeing here is based on the fundamental theorem of calculus. So the first part of it gives us the following statement. Basically, what we're trying to do here, by the way, is demonstrate the formal definition of a logarithm in terms of integrals. So remember, we use this notation. Lowercase f of x is a function of some kind. Capital F of x is the integral. Okay, so just remember, when you see capital F of x, this is the integral of f of x. And of course, you'll meet the c. So that's what this is meant to. Now, sometimes it's called an antiderivative, because you're just simply, it's the reverse operation of taking a derivative. So again, we have this case. There's a function over the interval from a to b. What f prime of x is the derivative of that integral, and that's giving me this area here. That's the first half of the fundamental theorem of calculus. So now the natural log of x, ln, is formally defined in the following way. Everything, whatever x is, you might recall that log of x looks like this. So here's the one. Let's say this is x. The integral. Oh, actually, I'm sorry. I'm drawing this incorrectly. Let's go to the next slide. I just realized this curve does not represent 1 over t. What you've got here is this. 1 over t looks like this. But if you notice, we don't need to worry about the third quadrant because the logarithm is only defined for positive numbers. So this is what we're after right here. So that being the case, this is, let's say x is greater than 1. Then whatever x is, the log of x is the area under this curve from 1 to that value. Okay. So for example, let's say we choose 3 for x. Let me see if I can draw this properly. So the formal definition is this. Log x okay. So imagine that I'd chosen 3. Okay. So in other words, don't forget the log of 1 is just 0. So this is really what it's telling us. In other words, you can visualize the log of 3 as simply that area under that curve from 1 to 3. They are the same thing. And this is taken from the fundamental theorem of calculus. Okay, now here's a few key properties. Now keep in mind too, the natural log is only, or any log for that matter, is only defined for positive numbers. In other words, it can't be 0, it's undefined. Log of 0 is undefined, but the log for any positive number is defined. Now, that being the case, the derivative of log x is simply 1 over x. Okay. The integral, on the other hand, of 1 over u, whatever u happens to be, is log u plus c. So in other words, u could be literally anything. It could be 3, it could be 17, it could be anything. So the integral, which sometimes you see it written like this, all right. Now, here's a few other things that we've already seen, but we'll review them again. For any strictly positive a and b, R is rational. The log of 1 is 0. Log of AB is the log of A plus log of B. Log of A over B is log A minus B. Log of A to the R power is R log A. Okay, now suppose, for example, you were confronted with the following. The derivative of a function of that log of x. Okay. Now we just got through seeing that d log x dx is simply 1 over x. But I just want to point out, we'll get to this eventually, but oops, sorry. No, we're good. This will hold for any function. It doesn't just have to be x. So what do we do here? Now, let me move this to the next slide. So here's our power rule for derivatives. You might recall this. If you have x to the n, you end up with nx to the n minus 1 power. But when this x is instead a function of x, that changes it a little, because now it's n g of x to the n minus 1 times g prime of x. Okay. Yes. So let me just show you a couple of quick examples here. Okay. So this is your g of x. Think of this as okay. That's what this is all about. So you've got the 2, the understanding that this piece is g of x. So you're going to have, let me just move it somewhere else where we have space. 2, 3, x squared minus 4 to the first times 2x. And then you can clean it up. I mean, you can simplify. You've got 2x, 2, that's 4x, 6, 12x. Because what's happening here is that the g of x is this 3x squared minus 4. The whole thing is squared. So you're going to have 2g of x to the first power times g prime of x. So the 2 is here. This is all g of x to the first power. Then you have g prime of x. That's the derivative of what's inside. Oh, wait a minute. You know what I just realized? No. You know what? I did something I shouldn't have. If g of x is 3 times x squared minus 4, g prime of x will be actually 6x. Because this function is actually, let me write this more cleanly, and then we can see where I made a mistake. Then g prime of x is 6x. Okay, so that means I've done this incorrectly. This should have been 6x. And so I actually ended up with 36 here. Okay, now we're talking. Okay, very good. So g of x is defined as the 3 times x squared minus 4 that means we're taking the derivative of gx squared. And therefore, what we're going to end up with is 2 times g of x to the first power times g prime of x. Okay, now we're good. All right, so this is sometimes called the generalized power rule. The chain rule is a consequence of this. So with natural logs, though, it's going to be a little trickier. The derivative of g of x. Now, the derivative of just plain old log x is 1 over x. So you can think of this as a special case where g of x is simply x. Okay, in other words, which means g prime of x is just 1. So you actually do have here g prime of x over g of x, but it's not obvious because it's just 1 over x. But now suddenly you're taking the log not of just simply x, but some function of x. We do need to explicitly consider g prime of x here. So let's say this is our original function. That implies that g prime of x by the power rule is 15x squared. So the derivative of the log of 5x cubed minus 2 is going to be 15x squared over 5x cubed minus 2, because this is g prime of x over g of x. All right, so that's on the next slide. To just be aware that this is g prime of x. So in other words, remember, if g of x is 5x cubed minus 2, g prime of x is therefore 15x squared. So now it's just straight ahead substitution. What about this one? Now, this one is a bit of a mess because we're combining 2 different things at once. Oops. But so yeah, you got 2 things going on here. Okay. The derivative of g of x, log g of x, is simply g prime of x over g of x. And the derivative of g of x to any power n is n g of x to the negative 1 times g prime of x. So how do we treat this one? Well, let's think of this as g of x is the log of 3x. Then g prime of x is we're going to have 3 over 3x. But we don't have the log of 3x. We have the derivative of g of x squared. Actually, I better be careful with this. This is just a one. Oh God. I have to be very, yeah, this is meant to be a one. And this is a prime. That's better. All right. So I'm gonna end up with or I can rewrite this as 6 log 3x over 3x. Or I guess I can reduce it to 2 log 3x over x. Oof, boy, that was a complicated one. We're going to need to do a lot of practicing. In fact, I think I'm going to make a note to myself next time. We're going to review a bunch of those. So we're basically combining a couple of rules here. That's why it's so complicated. So I do think we could probably use some more practice here. So I'll make sure that I write out a bunch of examples that we can work on. This is 2C. Before we dive into the rest of the material, I want to make sure we get this straight. Okay. So anyway, now this next one doesn't involve logs, but still, this one does require u substitution. So let's try u equals x squared plus 4 du dx is 2x, du is 2x dx. Now, did we do this correctly? Yes, because even though we don't have 2x dx, we can supply it ourselves. So 1/2 du. Now, you see what the connection with the logs is that this turns into du over u, which means it's just simply okay. So in other words, it might have looked like, wait a minute, why are we doing this example without logs? But this is the reason. Because once you've set it up properly, you'll notice that all you have is du over u, which means the integral is going to give us a log. Man. So the next section here, we're going to have a brief review of the properties of logs. And of course, we're going to define E in terms of integrals, just like we did with x, log x. So, all right, I'll tell you what, why don't we stop right here? And what I'll do is we'll grab some examples that we can practice before we go on to the rest of this material, because I think we definitely need some. And then the rest of this section, at least, is more of the same. We're looking at the definition of E. We're going to introduce some more complex derivatives using logs and e to the x. And then we'll see a few applications. So it's a very important chapter. Very important, or at least this part of it is especially important, especially if you're going to be doing this in any applied areas like any business application or economics. So we want to make sure we get this part right. And then in chapter 3, we're going to see some more complex techniques for taking integrals. So far, we've only focused on the substitution method, but there's quite a few others that we need to be familiar with. So, and that's going to take up all of chapter 3. So anyway, so we're really just getting into the really deep materials now. All right, so I'll see you all next time, and then we'll carry on from here.